do not determine. Instead, I'm not in process. So the other process, among the other process, then will determine the next process. So, and what about right now process? This is a 0. Process 0 is get the true, enter the critical section. Right now, process 0 is in the critical section. Then, process 1 would like to access the critical section. That calls the race condition. So then, process 1 is set as a true, which means I'd like to enter the critical section, but still not in the it's an intention. It expresses the intention to enter the critical section and check the other process, whether flag 0 is true or not. Right now, flag 0 is the other process. Process 0 in critical section is a true. So this is a true. So you cannot enter. You cannot leave the while loop. Okay? Wait. This is called the busy waiting. Okay? Until when? This one is set as other. Set as a 0 is a false. So check. Once this one is a false, this one will be false. Then you can leave the critical section and enter. You can enter the critical section. Okay. So this is another way to implement the critical section problem. So let's see. Mutual exclusion. How many processes? Only one process, so there might be no problem. Bounded time. What about the bounded time? Bounded time, maybe in this case, so if we have the two process, it will be the next one because it said I'm going to leave, then the other process can access the data. But the progress is even though I set as the I'm not in, okay? I'm not in. So two process, in case of the two process, it's okay. What about the three process? Three process case, so let's consider this one. Flag 0 and flag 1, both of them are true. Okay? Sometimes this one would like to enter this one would like to enter this. So who can enter? Because this is a true, this is a true. It may happen 3 or 4 process cases. Many processes would like to enter the critical section. And their value is always true, which means nobody can enter critical section in this case. So it's okay in case of the two process case, but in extreme case, if many processes would like to enter the critical section, nobody can enter critical section. So this one does not specify the next process, maybe okay, but sometimes it calls it may be waiting forever. So we can combine this algorithm 1 and algorithm 2. That is the Peterson solution. It's the first, not first, it's kind of the reference of the synchronization problem. You can consider both turn and flag. Turn we can explicitly determine because the algorithm 2, so using the flag, we can actually, we don't have to specify, but it may happen if all of them are true, nobody can enter. So what if we, to address that problem, combine the algorithm 1. Algorithm 1 we can specify using the turn variable. So we can consider both turn and flag. Okay? So turn is kind of globally all the processes determined. And flag means for each process who are in the critical section or not. Who want to access the critical section or not. Okay? Sometimes if you use only turn sometimes the process who doesn't want to access the critical section may be turned, right? That may cause a problem. Then that process never access the critical section, then the next one cannot be determined. So we can combine both of them, turn and the flat, okay? So that is the Peterson solution. So we can consider the same thing. If you are confusing the process I and J, you can consider 0 and 1, doesn't matter. So entry section is the combination of the flat I, okay? It's the same as algorithm 2. And turn, whose turn is that? Flat I means whether each process is in critical section or not. In other words, express I drive to enter critical section. And turn determine whose turn is that. Then how can we determine the whether we process can enter critical section or not? So flag J and turn J. What does it mean? In case this one is a false, we can enter critical section, right? If that is true, we cannot enter. So false means not this. Not this means not flat J, which means it's a false for other process 1. Or, because it's not, turn is not J. So two cases, or flat, so it's kind of combination of algorithm 1 and 2. Either turn is not the other process, or the flag. If I want access the data, then if other is a false, if other process not in the critical section, then I can enter. Even though it's not my turn, because no other process are accessing the flag, or no other process are intending to access the critical section, then I'm the only one, so I can access. Or if my turn, if not other process turn, which means it's my turn, then I can access the critical section. Then when I read, so if I determine, that is the too strong rule. Okay, so we are going to use the algorithm 2. Flag, who is the? I'm going to leave. I'm not in flag. I'm not in critical section. So let's check. Let's check the requirement. It's a mutual exclusion. Yes, only one process can access the mutual exclusion. Then this one, even though this one is two processes, both of them are true, because of the turn, you can access the data. You can enter the critical section. So it is also bounded waiting, okay, and it eventually progress. Okay, so that is the Peterson solution. Peterson solution is one of the oldest critical section problem, synchronization solution based on the software. It's just the algorithm. The main problem of the Peterson solution, this one, is it works with only two process cases. It cannot be generalized. So it's only the two process cases, but it can be used for understanding the synchronization problem. Okay? So mutual exclusion, okay, yes, definitely. And so at most one process can enter critical section, then after another. Because when a process leaves the critical section, it changes the flag, which means I'm not in. That condition will be used in the entry section of other process. Then other process, there are two options. Flag sometimes can be, both of them are true. We cannot address that. At the time, turn will be used to determine the other process. So that is the, I think I have the better slide. check. I have the better slide to explain that. Use that slide, that's much better. I have used before. When I find the slide, I will explain again later. I have the better slide that I made, but I lose that slide. Okay. So that is the Peterson solution, but that is based on the software solution. So we are going to see the hardware solution. Okay. So as I said, when we understand the synchronization problem, we can understand the synchronization problem as kind of the locking problem. So if we can apply the lock and enter the critical section, but also when we leave the critical section, we can release the lock. So, but the problem is how can we organize the next one, and how can we select the current process that among the processes who want to access the critical section. That is a key point to address that one. So to solve that problem, so we can use for the key of the lock as the hardware. Hardware solution is kind of the locking mechanism using the instruction. Then we can disable the interrupt. Then only the current process can access the critical section and enable the interrupt. The kind of instruction level, the implementation. So one is the test and set instruction. Test and set instruction. This is an instruction. What is the instruction, by the way? It's a
sequence of commands.
It's a basic processing unit, okay, by the CPU, which means you cannot divide the instruction level operation by two or segment, okay. That which means once it is selected by the CPU and processor should be completed. It's an atomic level. That is the key point, which means this looks like the software algorithm, but it's implemented in your processor level as the instruction. So instruction, who determine the instruction code? It's a processor, not your program, not your assembly language. Your CPU processor provide such an instruction code. So this is an instruction level code, which means the hardware. So what is the meaning, semantic of this test and set is such input is, there's the input value, and input value will be the return as it is, right? And you can set as such an input value as the true always. Which means if you test and set the flag is, for example, the current false. Okay? So this flag will be returned. Output of the test and set is false. Output of this one is false, but this value is changed into always true. That is the test and set instruction. Okay? So we are going to use this. Another instruction is swap. Swap is just exchanging the value. So we can use such a swap and test and set. So the basic is we can use the lock. Okay. So as I mentioned before. So log is a global variable for all the processes. So when you enter the critical section, you need to get the log. Okay, test and set. So log is, for example, the false over here. So which means nobody used the log. So if you call this one, output of test and set is the same value as this, false. So false means you can leave while loop, which means you can enter the critical section. And however, log value itself is changed into true. That is the test and set. At this time, if there is another process who want to access the critical section, and will execute the same test and set instruction log. What is the value of log? Currently true. Okay? So output of this instruction is true. True means you cannot leave while loop. It's a true. Waiting. Until when? When current process leave the critical section and change the value, this one, and get the log for this. Okay? So this is another solution for synchronization problem using instruction hardware layer. Benefit? It's very fast, right? Because it's an instruction layer. It's very fast, efficient. The problem, we need to check the three requirements are satisfied with this one. First, mutual exclusion, yes. Because only one process can get the log for this. What about the bounded waiting and progress? It's the same problem. Okay, it may cause the starvation problem. So because it relates the force, and sometimes only one process can get all the one. We cannot guarantee. We cannot guarantee bounded waiting. Okay. So that is the hardware solution. However, still, this one is very fast and can be used for the operating system that require high performance. Another one is the swap instruction that is I don't have to explain. The meaning of the swap instruction is changing the two value. Okay. So this is another solution. So we have the entry section and the exit section. So for the entry section, so we have the key. Okay, key is the true. Okay, that is the global variable. It's a boolean. So initialized as a false, and each process has the local, the boolean variable key. This is a local variable. Okay. We have the log, this is a global variable, this is a local variable. So key means my intention. I'd like to enter the critical section. I'd like to get the key. So it's express the intention. And why? So check whether key is equal to true, which means if the current process does not intend, you don't have to enter the critical section. Why key is true? Then, so I'd like to enter the critical section, so check this one. Then, if log is the false, the currently false, this is a false, I'd like to enter the critical section and swap. Swap means the key will be false and log will be true. Then this is the false. Then you can enter the critical section. However, if somebody already got the log, which means this is the true, then key is a true, log is true, this is a true, even though you swap, it's still true. So you cannot enter. You express, I'd like to enter the critical section, but still waiting until the other process, currently somebody log the critical section. At that time, the other process log set execute the exit the section, that is a log is a false. At that time, this is a force, then you can swap, then this is a force, then you can enter the critical section. Okay? So this is another way to implement the critical section. However, that solution, as you can imagine, do not satisfy with the bounded weighting. It's the same problem as the test and set, so it can be forever. So waiting forever. So we can address that problem by adding more the variable and the algorithm to the entry section and the exit section. Let's see. So, what time is it? Wait a minute. I try. So, this is the last slide. So, weighting. So weighting is a number of process. It's an array, and it's a local. For each process has whether I'm going to it's express. I try to enter the critical section. Okay, whether it's weighting or not, because the progress means what is the progress among the process who are not in the remainder section. In other words, those who want to access the critical section will enter progress to the critical section. This one, however, the other process does not have such a restriction. So that is the reason sometimes it's a hand, it's a star, and you can specify the other. To address that problem, to preserve such a progress, we are going to assign another the variable that is the weighting. So key is so each process, not globally, each is a local variable. Each process would like to enter the critical section. Okay. Then we will check the both the weighting and key. So let's see. So this one, if you consider key, that is the same as a swap, and or the test and set. Okay, the previous algorithm. Because of this one, only consider whether this is the process to enter this one. So we cannot guarantee the bounded weighting. So that is the reason we have another option, that is the weighting. So if this is a force, we can enter the critical section. This is a critical section part. So actually this part is considered this. So, but this one is just a setting. I'm not waiting because I entered the critical section. So what is the condition to enter, to leave this one? That is weighting is not. Weighting is force or key is force. Okay? So if the key is a force, that is the same algorithm as the previous one. Okay? If you swap or the test and set the key, that time you can enter the critical section, which means that the other process, the lead, change that one using the lock. Okay? That is the same. And another one is weighting, because I'm weighting. So, but if this one is not, so if this one is force, and this one is true, and weighting I. Okay, this time the beginning time is not possible. We will see it later. So using test and set is the same as the previous one. So in cases F is changing with the test and set. So if the lock is a force, it will be changed into the force. Then weighting is the force. We are not weighting. This one will be used for exit section. During the exit section, we are not going to consider force. I'm not the part of the selection during the exit section. Then how can we select the next one? next process. But next process may not wait. At that time, while loop until there exists a process who is waiting. Then that process will be selected. What is the worst case? It's the number of processes who are waiting for that. So you keep checking until end of process. If not, there's no other process, and also it's not, then you can say the waiting is not full. Okay? This process, if there is a that process, will be false. That means because of other process, this one will enter that. So mutual exclusion, yes. Bounded waiting is just one round of the selection. It's a bounded waiting. And among that, only we consider waiting the process. So that's satisfied with the progress also. So this is the critical section problem solution using hardware. That is a TestAndSet Instruction. That satisfied with the three conditions. Okay? So that is here. The next class we will see the operating system solution for the synchronization problem using semaphore. Semaphore is the very important data structure, so we will see next class.